Hi everyone, my name is Matt, and today I'm going to walk you through a short project where I used natural language processing to analyze Baxter International's 10K filings from 2007 to 2009. This is my first demo, so I'm genuinely excited to share it. And the goal of this recording is twofold. First, to keep myself motivated and make my thinking more structured. And second, to showcase to recruiters the technical and analytical skills I've developed through this project. Okay, so let's get started. Let's get started with some quick context. In April 2010, the FDA announced stricter regulations on automated pumps, devices that deliver food and medication to patients. Shortly after, in May 2010, Baxter voluntarily recalled one of its key infusion pumps due to battery failures and software issues. That caught my attention. I wanted to know, was there any early sign of this in Baxter's 2009 annual report? Could we use language analysis to detect shifts in tone, content, or focus before the public recall happened? So to explore this, I downloaded Baxter's 10K filings from 2007 to 2009. For clarification, since 2009's report was published during 2010, I will just call the 2009 report filing 10, and you can see in the matrix later. To start a project like this, the first step is always to have a clear structure in my mind for how you're going to approach it. So, using a top-down, bottom-up strategy is often a good idea. In this case, I'll begin with the bottom-up approach, starting by thinking about what model or techniques I plan to use. Based on that, I can determine the most suitable data preprocessing methods, and that is called top-down. So data preprocessing is always the first hands-on step, but the choice of method often depends on a model or a strategy you've decided on. So that's why you should combine top-down with bottom-up. So so here is the data preprocessing step one. So why did I build this function to do data preprocessing? So basically, when you are working with 10K or 10Q filings, there are a few sections that are really important, like item one, business, item 1A, risk factors, item 7, MD&A, and item 7A, quantitative disclosures. So these parts usually tell us the most about how a company operates, where the risks are, and what management is thinking. But the problem is these filings are super long and messy. You know, the TXT file just collect everything and it's really messy. So especially when you are dealing with hundreds of them. So manually copying and pasting is just not realistic. So I built this function to automate that, to quickly and cleanly pull out just the parts I care about and make the rest of the analysis easier. So how I realized it? First, I load the entire text of the filing. It's usually a raw text file. Then I use regular expressions to search for the section's headers, like item 1A or item 7. For each section, I look for the start and end points in the text. And since formatting can be messy, I make sure to get the longest possible match between those markers. So that way, even if there are duplicates or formatting issues, I still capture the full section. Each section gets saved into a dictionary with its label, like business, risk, or MDA, so I can access them individually later. And if something goes wrong, say the section isn't found, it just skips that one and moves on. So the rest still works. So that's basically the logic of my code. Yeah, also I use RE to like do some search and findings. You can see it's pretty long code here. Then I just use my function to get them itemized 10K filings from 2007 to 2009. And you can see here, that's the result. like business, item one, you get business, and all the text is related to that four sections. So after extracting key sections from the filings, the next step is text cleaning. So raw financial text contains noise, like punctuation, numbers, and common filter words, which can interfere with analysis. So this clean text function handles that by performing five steps. The first is to convert all text to lowercase. Uh, and second, removes punctuation and numbers. And third, collapses extra white space. Four, removes stop words using NLTK's English stop word list. And five, returns to a clean, space-separated string of meaningful tokens. So we apply this function to each section of each filing, filing 10, filing 9, and filing 8, so that the data is normalized and ready for further preprocessing and like also for further analysis like vectorization or similarity analysis. Then yeah, we start to use word level tokenization to do some cosine similarity analysis. So in this step, I applied a simple bag of words model using content vectorizer with a word level tokenization. So each filing was first converted into a single string by combining its linked sections. Then content vectorizer tokenized each document into individual words and transformed them into count vectors representing how often each word appears. So with these document vectors, I computed pairwise cosine similarities to measure how semantically close the filings are. As shown in the similarity matrix, filing 9 and filing 8 are highly similar with a cosine score of, you can see here, 0.979. Like filing 10 is some more different, indicating risk, especially from filing 8, which shows a lower similarity of here 0.716. So this suggests some language or content shift in filing 10 compared to earlier years. Then I use n-gram tokenization with both unigrams and bigrams. Unlike word level tokenization, which only looks at single words, n-grams capture short word sequences. If there is a sentence like, here is the revenue growth. So it will capture not only the single word, but also a short phrase, such as it will capture like the word here and is and the and revenue and growth. And also, if you use like 2 gram, it will also capture here is the revenue and revenue growth. So that's the basic difference about it. So which adds context and meaning. This gives the model a better understanding of phrasing and word combinations. So the similarities results overall are very similar to the unigram case, with filing 9 and filing 8 still the closest, and filing 10 are different from earlier years. So then after that, I use TF-IDF instead of raw word counts. The key difference is that TF-IDF downweights common words and upweights words that are more unique to each document. This gives a better sense of what makes each filing distinct. The similarity results remain consistent with previous method. So after that, in this step, I used doc2vec, which learns a dense vector for each entire document instead of relying on word counts or frequencies. Unlike TF-IDF or bag of words, doc2vec captures semantic meaning by training the document vector to help predict surrounding words. So the output vector reflects the overall context of the filing. Once trained, we extract the document vectors and compute cosine similarities. The results are consistent, also consistent. Filing 9 and filing 8 is still the most similar. So I also retrieved the top words most similar to each document vector, which helps interpret what each filing focuses on. You can see here top words categorizing each filings. Like you can see here, filing 9 and filing 10's word, we can find some similarities, but filing 10 some shifts indicating risk, right? So to wrap up, I tried four different ways to measure how similar these filings are. There are bag of words, n-grams, TF-IDF, and doc2vec. So each method has its strengths. Bag of words and TF-IDF are, simple and fast, but they only look at word frequency. So n-grams add a bit more context, and doc2vec goes further by learning the meaning behind the text. So across all methods, the results were pretty consistent. Filing 8 and 9 looked the most similar, and filing 10 similarity with others is the lowest. This did indicate the potential risks, like I said, the context before, some recall on the pumps. But we should be careful here. So these scores mostly reflect how similar the wording is, not necessarily the content or idea is. So if we want deeper insights like whether management tone or strategy actually changed, we need more powerful tools, some models like Finbert or sentence embeddings that understand context